You are listening to The Vocal Technologist. Spoken tech for your ears.
Tools are getting faster, trust is getting lower. Both are true.
Yeah, that is, it's pretty much the absolute defining tension of engineering right now, isn't it? You can build at absolute light speed, but you're constantly looking over your shoulder, just waiting for something to inevitably break.
Right. And if you're trying to figure out how to navigate that mess without your entire infrastructure falling over, well, you're in the right place. Welcome to Vocal Technologist.
Glad to be here.
So we're going to have a proper look at how the industry is forcing AI agents to finally grow up, follow the rules, and untangle the pretty brutal realities of scaling the infrastructure that actually supports them.
Because we're well past the honeymoon phase with AI, I reckon. It's time to get the architecture right, mostly because the stakes are just too high now.
Yeah, exactly.
Yeah.
So the bit rattling around my head is how the hardest part of our jobs just isn't writing code anymore. I mean, think about it. Writing code used to be the primary physical constraint. You had an idea, you had to type out the logic, test the syntax, and that took hours or days.
Heaps of time, yeah.
But the economics of software engineering have just completely flipped on their head.
They really have, because, an AI can generate a patch or spin up a really complex Python script in seconds, right?
Yeah.
So the main cost of small engineering changes has totally moved.
Right.
It's no longer about the effort of implementation. The sheer cost is now in reviewing that code and, well, more importantly, owning it once it's actually sitting in production.
Spot on.
Yeah.
A generated patch is fantastic for validating scope. You get this concrete evidence of what a feature might look like instantly.
Yeah.
But it forces human judgment into a totally different, much more stressful corner, I reckon.
Yeah, absolutely.
Because when you're reviewing an AI's pull request, you're not looking for a missing semicolon. You're looking for subtle logic bombs. You're thinking about risk, maintainability, long-term ownership. You're essentially, pricing uncertainty.
And that uncertainty just multiplies exponentially when you start letting AI act autonomously. Like, it's one thing for a bot to politely suggest code in your editor.
Yeah, that's harmless enough.
Right, but it's another thing entirely when it's committing code, running tests, and pushing to production on its own, which is exactly why this whole concept of identity is becoming so critical. If a bot writes the code and a bot deploys it, who actually owns the consequence when the database gets wiped?
Which brings us perfectly to what Block is doing. I was poking around their open source workspace, Buzz, and the premise is genuinely wild. It's a self-hostable community where humans and AI agents literally share the exact same rooms.
Yeah, it forces the issue of identity right out into the open. Because in a lot of platforms, an AI is just this faceless API integration that dumps text into a Slack channel, right?
Yeah, just a glorified webhook.
Exactly, but Buzz is built on a Nostr relay event log.
Right, and for anyone who hasn't had a chance to suss out Nostr, it's a decentralized protocol. There's no central server controlling everything. Instead, every single action is treated as a cryptographically signed event.
Spot on. Every message, every code patch, every workflow step, and every review approval is a mathematical proof tied to a specific key pair. And here's a crucial part. The identity model is exactly the same, regardless of whether the author is a human being or a background AI process.
So they're on equal footing. We're essentially giving the bots a staff badge and an HR file. And that's where I get genuinely skeptical. If they have the exact same affordances as human teammates, how on earth do we govern them?
It's the big question.
Because if I push dodgy code that takes down production, I have to answer for it. If a bot does it 10,000 times a second, who gets fired? You can't just politely ask an LLM in the system prompt to, please behave and don't delete the production database.
No, you definitely can't. That's the exact fear keeping security teams awake at night right now.
Yeah.
Probabilistic guardrails just fail. You can't rely on the AI's internal logic to follow the rules because, well, LLMs are fundamentally unpredictable. You need deterministic governance.
So how do you actually cage it? Because clearly putting a sticky note on the server saying, bots, please be careful, is a bit ordinary.
Yeah, a bit ordinary and highly dangerous. You have to wrap them in structural boundaries. So look at something like Microsoft's Agent Governance Toolkit, or AGT. It's an open source library specifically built to enforce policies and create immutable audit trails for autonomous AI agents.
And the beauty of it is that it spans across languages, right?
Right.
Like Python, Rust, Go. You're not locked into one specific AI framework just to get some basic security.
Yeah, it integrates everywhere. But the real genius of AGT is where it intercepts the agent's actions. It doesn't sit inside the AI prompt. It operates at the application middleware layer.
Okay, let's get into the guts of that for a second.
Yeah.
Operating at the middleware layer means it sits right between the AI's brain and the actual system tools it wants to use.
Precisely. Before the AI can actually invoke a command to, say, write to a system file, alter a database, or call an external API, AGT intercepts that tool call. It checks the cryptographic identity of the bot, verifies the policy permissions, and just blocks the action entirely if it violates the rules.
So blocked actions are structurally prevented, not just, probabilistically discouraged. You aren't relying on the AI to understand the company rulebook. You're wrapping it in a physical barrier.
Exactly. The bot tries to execute a dangerous command, and it hits a literal brick wall before the system even sees the request.
Which is brilliant. It's the only way to scale trust with autonomous systems. You give them a real identity so you know exactly who is doing what, like Buzz does with Moster, and then you wrap their actions in structural governance that cannot be bypassed, like AGT does at the middleware layer.
But, giving bots an identity and a strict set of rules is really only half the battle, isn't it?
True.
Because if they can't communicate reliably with the rest of the system, it's all completely useless. Which brings us to how these AI agents actually talk to the network.
Yes, and this is where we're seeing a massive architectural shift with the Model Context Protocol, or MCP. The entire protocol is going stateless.
Which is huge.
It really is. To really understand why this matters, we kind of have to talk about how MCP originally worked. It relied heavily on stateful sessions. And if you've ever had to manage a distributed system, you know that state is basically the enemy of scale.
Oh, absolute enemy. Stateful sessions meant you needed sticky sessions behind your load balancer. So imagine a user, or in this case, an AI agent, talking to a backend server.
Yep.
If the connection is stateful, the client has to keep talking to that exact same server instance for the entire conversation, just because that specific box holds the memory of everything they've discussed so far.
Which is an absolute nightmare from an infrastructure perspective.
Yeah.
Because if that specific server instance crashes, or you get a massive spike in traffic and need to scale up quickly, you're in real trouble.
Yeah, you're stuck.
You can't just route the AI's next request to a new server because the new server has no idea what the AI is talking about. It just creates these massive bottlenecks.
It completely defeats the purpose of cloud elasticity. So the new MCP spec drops stateful sessions entirely, right in favor of stateless HTTP.
Meaning every single request carries its own context with it.
Exactly. It uses a metadata object passed with every single API call. So remote MCP servers don't need sticky sessions anymore. They don't need complex shared session stores like Redis just to keep track of a chat.
So no instance coordination at all.
None. Any server instance in your entire fleet can handle any incoming request from any agent at any time.
That's a massive maturity milestone for AI infrastructure, honestly. It means we can finally treat AI traffic just like standard web traffic. But they didn't stop just fixing how the data moves, did they? They also completely gutted the observability side.
Well, they had to. If you have hundreds of autonomous agents pinging stateless servers thousands of times a minute, you need to know exactly what they're doing. So MCP replaced its proprietary logging channel with open telemetry.
And they standardized request tracking using W3C trace context. I mean, I cannot overstate how important this is. The W3C trace context basically acts like a global tracking number for a package.
That is a great way to put it.
When an AI agent makes a request, it gets a unique ID. That ID gets passed along to every single database, API, and microservice that the request touches.
Which means you can finally correlate an AI agent's tool calls with the rest of your application stack. You aren't just guessing what the bot did in some isolated silo anymore.
Right.
You can see its actions in the exact same observability dashboard as your database queries and your front-end rendering times.
And for anyone who isn't living in the monitoring world, OpenTelemetry officially achieving CNCF graduated status is monumental. The Cloud Native Computing Foundation is the governing body for this stuff, and graduated status puts OpenTelemetry on the exact same elite tier as Kubernetes and Prometheus.
Oh, yeah. We're talking over 12,000 contributions from more than 2,800 companies.
It's massive.
It originated from a merger of two competing standards years ago, and now its traces, logs, and metrics are entirely general availability. It really has become the definitive, undisputed standard for seeing what your code is doing in production.
It's like we finally stopped letting the AI use a dodgy custom walkie-talkie and forced it onto a global telecom standard. If an AI agent hallucinates and triggers a massive database query that slows down your website, you just don't have to guess what happened.
The visibility is total. You can trace a failure from a back-end database timeout through the middleware all the way back to the specific LLM prompt that triggered it.
If you reckon this kind of architectural teardown is useful, hit subscribe so we can keep bringing it to you. Right, so we can track the bots and we have the communication protocol sorted, but let's actually look at the infrastructure that's taking all this traffic.
Yeah, let's.
Because no amount of AI governance saves you from a fundamentally ordinary architectural decision.
You're pointing directly at the reality of microservices, aren't you?
I absolutely am. We've spent years treating microservices like this mandatory technical upgrade. There was this prevailing attitude that if you aren't building microservices, you're just building legacy garbage.
Which is a complete misread of why microservices even exist in the first place. They are primarily organizational boundaries. They are not a technical silver bullet.
That is such a critical distinction. We tend to forget Conway's law, the idea that systems just mirror the communication structures of the organizations that design them.
Exactly. When a company adopts microservices, they're usually solving a people problem, not a code problem. Microservices let individual teams own specific components.
Right.
Team A can own the checkout service, and Team B can own the user profile service. They can release their code entirely independently whenever they want without waiting for a massive, company-wide, monolithic release train. You get incredible autonomy.
But you pay a massive, brutal tax for that autonomy.
You pay with duplicated infrastructure. Every single microservice needs its own CI/CD pipeline, its own logging, its own security rules. You pay with distributed systems complexity. Debugging becomes exponentially harder because a single user request might jump across 15 different services before returning a result. And the coordination costs, just figuring out which service talks to which and who owns what, it goes completely through the roof.
You are essentially trading code complexity for operational complexity. And the harsh truth is that microservices are really only valuable when your organizational scale is so massive that you have absolutely no choice but to accept those trade-offs.
Yeah, if you have 5 engineers, microservices are probably having a lend of you. You're just making your life harder for absolutely no reason.
Too late.
But if you have 500 engineers, they are a survival tactic. You literally cannot have 500 people committing to the same monolithic code base without tripping over each other every 5 seconds.
Which makes managing that infrastructure at scale utterly terrifying, honestly. But there are ways to do it right. I was reading about Pinterest's resource provisioner pipeline, and it's just a perfect example of managing organizational scale without losing control of the technical reality.
Oh, Pinterest is a textbook example of wrangling massive sprawling complexity. I mean, they had to figure out how to let hundreds of engineers spin up infrastructure without causing an absolute security disaster.
Right.
So their solution was to centralize their Terraform execution.
Just to put this in perspective for you, we are talking about centralizing infrastructure deployment across hundreds of workspaces and tens of thousands of AWS resources.
It's staggering.
And all while preserving team ownership in a multi-repository environment. Wait, tens of thousands of AWS resources across a multi-repo environment. That sounds like an absolute nightmare to audit.
It would be, but the way they enforce least privilege across all those resources is brilliant. They use GitHub OIDC OpenID Connect.
Let's unpack this for a second because it's a massive security upgrade. Historically, if a deployment script needed to talk to AWS, you'd just give it a static API key.
Yep, the old way.
But static keys get leaked, they get accidentally committed to public repositories, and then you're mining crypto for a hacker in about 5 minutes.
Exactly. OIDC fixes that entirely. Instead of long-lived static credentials just sitting around waiting to be compromised, GitHub and AWS establish a trust relationship.
Right.
When the GitHub action runs, it essentially asks AWS for a temporary, short-lived token, mathematically proving its identity. As soon as the job is done, the token expires. Poof, gone.
And they pair that with this incredibly strict repository path to workspace mapping.
That is the absolute core of their governance. A specific file path in a GitHub repository is strictly, immutably mapped to a specific Terraform workspace.
Okay, so Team A can only deploy changes to Team A's infrastructure.
Exactly. Because the pipeline literally will not allow their code to execute against Team B's workspace. You cannot deploy infrastructure changes outside of that mapping, and they combine that with back-end validation, heavily downscoped IAM roles, and mandatory human reviews.
That strict path to workspace mapping is actually a brilliant way to cage the beast. I mean, it forces order onto the chaos.
It allows the central platform team to perform consistent auditing, automated security scanning, and company-wide fixes. If there's a new security standard, the platform team enforces it in the central pipeline.
Yeah.
The individual product teams still write the Terraform code for their specific microservices, but the platform dictates exactly how, when, and where it gets executed.
It's the ultimate balance. You give teams the autonomy of microservices so they can move fast, but you retain the centralized governance of a monolith so the whole company doesn't fall apart.
And it all just comes down to understanding and choosing your trade-offs. Just like microservices are an organizational trade-off, at the lowest architectural level, even the databases we rely on every single day are just a series of expensive compromises.
Oh, let's talk about the database tax.
Yeah.
Because there is a very loud, fairly fiery critique going around engineering circles right now that PostgreSQL's MVCC is fundamentally flawed.
Right, MVCC being multi-version concurrency control. To really understand the critique, you have to understand the problem it actually solves. If user A is reading a row in a database and user B is trying to update that exact same row, you don't want them to block each other. MVCC is how Postgres handles multiple transactions happening at the exact same time without locking up the entire table.
But the core argument against it is that Postgres stores old row versions directly in the main table. So if I have a user profile and I update my email address, Postgres doesn't just overwrite the old email, does it?
No, it rates a completely new version of the row with the new email and simply marks the old row as dead.
Which creates a cascade of consequences. You get write amplification because every update is essentially a full insert, and more importantly, you get severe table bloat. If you have a system with high update volumes, like, say, a live analytics counter, your table grows massively with all these dead rows.
And that leads to the infamous vacuum pressure. Because all those dead rows are taking up space, Postgres has to constantly run background vacuum processes to sweep through the tables, find the dead rows, and reclaim the disk space.
Which can be brutal.
Oh yeah, if your vacuuming isn't tuned correctly, or if it falls behind, it can literally bring a production system to its knees. So the critique is entirely valid. MVCC in Postgres creates real maintenance overhead.
But here's the crucial context that often gets missed by the loudest critics, I reckon. Every single database engine has this concurrency problem. They just hide the cost differently.
Exactly. It's a fundamental law of physics for databases. You cannot have high concurrency reads and writes without paying a tax somewhere in the system.
Right. Look at Oracle or MySQL's InnoDB engine. They handle it differently. They don't bloat the main table with old versions. Instead, they use massive, complex undo logs to reconstruct historical data on the fly for active readers.
Which keeps the main table clean, yeah, but it shifts the performance tax heavily onto the writers and onto the readers who actually need that historical data.
And SQL Server puts immense pressure on its version store in template, which can cause entirely different cascading failures.
And MongoDB consumes vast amounts of memory cache and history storage just to manage concurrency. And if you look at LSM databases, log-structured merge trees like Cassandra or RocksDB, they just defer the cleanup completely to a background compaction process, which can cause massive I/O spikes when it finally runs.
So MVCC isn't a unique problem that anyone else has actually eliminated. It's just an architectural choice about who pays the tax and when they pay it. Postgres makes you pay in table bloat and background vacuuming. Oracle makes you pay in undue log contention.
The trade-off is inescapable. You just have to pick the poison that your specific workload can tolerate best. If you have a read-heavy workload, Postgres is phenomenal. If you have a system that updates the same rows 10,000 times a second, you might feel the MVCC pain pretty sharply.
I love that perspective. It completely strips away the magic. Everything is a compromise. But just to completely contradict myself here, sometimes a piece of tech comes along that just decides to break the speed limit entirely and ignore the usual trade-offs.
You're looking at Zig.
I am absolutely looking at Zig. For anyone who hasn't seen it, Zig is a systems programming language, and their approach to increments compilation is just staggering.
It's a genuine masterclass in performance engineering. When you compile a complex application in most languages, usually the compiler has to do a massive amount of redundant work.
Right.
It ends up reparsing and analyzing files that haven't even changed just to make sure everything links up correctly.
But Zig compiler doesn't do that. It tracks source hashes, essentially creating a fingerprint of your code. And from that, it builds a massive declaration-level dependency graph.
It basically draws a map of your entire code base.
Hmm.
So when you change a single line of code in one file, the compiler knows exactly which specific functions are downstream from that chain.
That's so smart.
It only reanalyzes and regenerates the specific functions touched by that modification. Everything else is completely ignored.
But the truly wild part is what happens next. They use a tightly integrated incremental linker. It doesn't take all those pieces and rebuild the executable binary from scratch. It takes the newly updated machine code and patches it directly into the existing binary file on your hard drive.
In place.
In place. It enables rebuilds of complex, heavy applications in roughly 50 to 70 milliseconds.
The human brain can barely even perceive a delay that short. You hit save in your editor, and the new binary is already compiled and ready to run before you've even moved your mouse.
That isn't even a rebuild. That is basically performing open-heart surgery on the code base while the patient is still walking around.
It fundamentally changes the feedback loop for developers. When compilation is that fast, writing a low-level systems language suddenly feels like you're writing in an interpreted scripting language like Python or JavaScript, but you retain all the raw performance and memory safety guarantees of a compiled systems language.
It just proves that while most of engineering is about managing painful trade-offs, like we saw with microservices and Postgres, there is still room for sheer brute force innovation that just makes things objectively better.
If you look at the through line of everything we've talked about, it all points to one undeniable thing, I reckon: maturity.
The industry is finally growing up.
It really is. Whether we're forcing AI agents to drop stateful connections and use robust stateless HTTP, or wrapping them in deterministic middleware governance toolkits so they can't blow up production, or whether we're admitting that microservices are just an org chart solution with a massive coordination tax, or just acknowledging that every database is a different flavor of compromise.
We're trading the hype for actual disciplined engineering. We're looking at the harsh realities of scaling and saying, okay, how do we actually govern this? How do we audit tens of thousands of AWS resources securely? How do we trust an autonomous agent to actually follow the rules?
The foundational building blocks are finally being put into place to answer those questions. OpenTelemetry gives us the visibility across the entire stack. Toolkits like AGT give us the hard boundaries.
Yep.
Protocols like the new stateless MCP give us the standardized, scalable communication.
It's all coming together to make this stuff actually viable for the long haul. But, you know, it does leave you wondering where the edge of this goes. If we're giving AI agents their own cryptographically signed identity models and immutable audit trails now, how long until an AI gets assigned its own dedicated staff engineer just to clean up its technical debt?
Oh, that's a terrifying thought.
Think about that one next time you blindly approve an AI pull request. Vocal technologists, see you soon.
Spoken Tech for your ears.